G'day, Section 2. Thanks for joining me again as we learn to integrate some more stuff. Before we get into that, here is a flashback question that you should already know how to do. We have the integral of x squared over 1 plus 4x squared. This is plagiarized from the 2009 HSC paper and it was a 3-mark question. Pause the video, see if you can figure it out. Alright, so the way we tackle this one is we chuck a 4 up the top and write it as a 4x squared. So we put a quarter out the front. The reason I'm doing this is because we're going to apply the techniques that we looked at in the last video where we split apart the numerator. Okay, so I'm going to write the top as 4x squared, and now I'm going to write it as 1 plus 4x squared, take away 1. Okay, the reason I've done that is because now I can see I've got the top and bottom sort of matching, so when I split it all apart, stuff's going to cancel off and life's going to get easier. So let's do that next. We split apart the fraction, okay? So we put the minus 1 in its own fraction, and now 1 plus 4x squared over 1 plus 4x squared is just 1. So all we've got to figure out now is how to integrate 1 over 1 plus 4x squared, okay? Because I'm hoping you can integrate 1, even I can do that. So staring at this, what's the best option here? We need to use inverse tan, okay? It kind of looks like a over a squared, a over a squared plus x squared. We can make it look a bit nicer by doing a substitution. We can let u equal to 2x, so that this whole thing down the bottom is going to become u squared. Of course, don't forget to change your du on dx. So you do u equals 2x, so du on dx equals 2, and then you swap the dx and the 2, and you get the dx equals du on 2. So we're going to change this dx to a du on 2. We're going to change the 4x squared to a u squared. Okay? So just substituting, putting in our information, and it looks like this. And now I can just put that half out the front and make that an eighth. And now you're all good, okay? We can integrate 1 as just x, and we can integrate this as inverse tan of u, keeping in mind that u is actually 2x. All right, so we end up with this. Quarter times x minus an eighth times tan inverse of 2x, or u, okay, same thing, plus your constant. All right, so it's a little bit tricky, but if you can see that you can split this apart, once you get to this part, this line here is not too challenging, okay, as long as you know how to handle inverse tan. All right, cool. So last week we were looking at splitting apart numerators. Today we are tackling how to split apart denominators using a technique called partial fractions. Okay, very, very important. I would say it's not a massively hard concept, but there is a bit of work and there's a lot of room for error because there's a few steps to these. So this might be a bit of a long video today. All right, for our first example, we are going to hypothesize that there is some way of writing 5x over x squared minus x minus 6 in terms of these two fractions. Okay, so in year 11, you would have learned to combine two fractions by cross multiplying and end up with this. Today we are trying to work backwards, which is a lot trickier. Okay, so first things first, and then once we do that, integrating this is going to be much easier if we can integrate it in this form. Okay, so we're trying to find the constants a and b that make this equation work so that we can integrate this right hand side rather than this left hand side. Okay, for these questions you'll quite often see this symbol here. Instead of writing equal to, they use the 3 horizontal strokes, which means mathematically equivalent to. Kind of means the same thing as equal to. I don't know why they don't just use equal to. It seems needlessly confusing and I don't really know why, so let's not discuss it much further. All right. So here's how we approach it. We try and make the left-hand side and the right-hand side look the same in terms of the denominator. So we're going to combine these two fractions, okay, as you would in year 11 with a bit of cross multiplication. Okay, so now we have a times x plus 2 plus b times x minus 3, and now we have the same denominator. Okay, I'm hoping getting from that to that is something you can do in extension 2. I hope we don't have to explain that too much. Okay, now looking at both sides, we have on the bottom, the denominators are both the same. So if these two are going to be the exact same, what we're really comparing is the tops. We need this top to be mathematically equivalent to this top. So once you've made the two bases match, you can just ignore them and just say, well, I just want 5x to be equal to a times x plus 2 plus b times x minus 3. So now we need to figure out what a and b are. Okay, so the way we do this is we pick and choose clever or convenient values of x to substitute into this equation. And by convenient, I mean a value of x that's going to make some stuff disappear. So looking at this, I can see that if I subbed in x equals -2 to both sides, this term would vanish and I can solve for b. Okay? Or if I subbed in x equals 3 to both sides, this term would vanish and I could solve for a. So first thing we're going to do is take this equation, both sides, and we're going to sub in x equals -2. Alright, here's what we get. On the left, we'll get 5 times -2, and on the right, like I said, we have -2 plus 2. This is 0. We don't know what a is, but it doesn't matter because anything times 0 is just gone. Okay, and here we have -2 minus 3, so we have -5b. So conveniently, the a's are gone for now, and we can just solve the equation for b and get an answer of 2. Alright, so we're halfway there. We've got the b, we just need the a now. So now we choose another clever, convenient value, and like I said, it's going to be x equals 3. We're taking this equation, substituting in x equals 3 on both sides, and here's what we get. Alright, we get 5 times 3 on the left, we get a times, it's going to be 5, isn't it? And then this one, like I said, is just 0, so it's gone. Even though we know now that b is 2, it doesn't matter. Either way, it's going to disappear. And we end up with 15 equals 5a, so therefore a must be equal to 3. Alright, cool. That is the hard work done. Now we just go back to the top line, and we change this a and b to 3 and 2. Alright, and now if we need to integrate this left-hand side, we can just integrate the right-hand side by writing it in the more convenient way. Okay, now these are very simple linear terms. If we want to integrate these, all we need to apply is simple logarithms, and hopefully you guys can see why that's pretty straightforward. As always, don't forget your absolute values, don't forget your constant, but there is your answer. Okay, the way these questions work is that usually the integration is simple, and that's why we do this. Okay, so it's a bit of work to set up your fractions, find your constants, but if you've done it correctly, you should break the fraction into something that is very simple to integrate. Okay, most of the time it'll involve logarithms. The tough ones will involve a bit of inverse tan. Okay. All right, for our next one, so we're going to do more practice with that. If you think that made sense to you and you can follow that pattern, I encourage you to pause the video and see if you can try setting up this one. We're going to do a partial fractions breakdown again. So we're going to write this as 2 simpler fractions. So first thing we do is we're going to factorize the bottom of the fraction, writing this as x plus 2 and x minus 1. And now again, we are hypothesizing that there is some simpler way of breaking this apart into 2 separate fractions, okay, where a and b are constants. All right, so again, we combine the 2 fractions on the right so we can make the denominators the same, so we can just compare the tops. So we're going to combine these 2 fractions with cross multiplication, a times x minus 1, blah, 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 same as last time. Now that we got the denominators matching, we can say, well, if these 2 are going to be equivalent, the tops need to match as well. So we set 3x equal to ax minus 1, bx plus 2. Now again, we look at our expression and we say, what are some convenient values I can substitute in? I can see x equals 1 and x equals minus 2 as convenient in making stuff disappear. So first thing we'll do is sub in x equals 1. So on the left we'll get 3, and here we get 0 plus b times 3. So we'll get 3 equal to 3b, which means that b needs to be 1. Awesome, only one value left. We're going to solve for a by subbing in x equals minus 2, so this term is gone. So on the left we get 3 times minus 2, so we'll get minus 6. The b is multiplying by 0, and we've got a multiplying with minus 3. Solving that, we get that a is equal to 2, and then once again, that's the hard work done. Now, a is 2, b is 1, and so we can just integrate these 2 fractions up here. Okay, so I'm just taking the top line, and I'm just writing it as a partial fraction breakdown, and now we're going to integrate these 2 fractions separately, again with simple logarithms. don't forget your constant. All right, and that's all it is. Let's move on to the next one. Okay, a bit more complicated now, because in the last example, both our pieces on the bottom, both our parts, I guess you could say, were both linear. And when I say linear, I mean just x's, okay? Pretty simple terms. In this one of our parts is going to be, it's going to be squared, so it's going to be a quadratic. It's going to be degree 2 rather than degree 1. That does change this, okay? So here's our setup. We are hypothesizing we can write this fraction as a breakdown of these two parts, of these partial fractions, okay? So in this first part, I've got x minus 2, so on top I've got a constant. But the reason here that I've got a constant is because the top is always going to be a degree less than the bottom, okay? Just trust me on that, it always works out. I can show you why when we're back in class, but for now we're just going to focus on the doing. So on the bottom we have a degree 1, so on the top we have degree 0, which is a constant. With this part here, on the bottom we have a quadratic, which is degree 2. So on the top we're going to have a generic degree 1, which means linear. Okay, so we've got a squared on the bottom, so we've got an x on top and a constant. Okay, if I had a cubed on the bottom, you'd virtually never see it, but if I did have a cube down here, up top I would have cx squared plus dx plus e. Now you may be wondering at this point, why do I have a, c, and d? The reason for that, the reason that b is missing is because I'm an idiot and I didn't realize until I finished the entire question and I couldn't be bothered changing 40 slides. Okay, so sorry that b is missing. I'm sure that upsets you. It really upsets me, but this is the hand we've been dealt, so let's just keep moving forward. Okay, apart from that, the setup is different, but now the process is the exact same. Okay, and it is worth mentioning that in quite a lot of partial fractions questions in the HSC, I would say more than half, this first line is often done for you. Okay, so quite often these are two-part questions. Part 1 is write this, find the constants a, c, and d such that this works. Okay, and then part 2 is hence integrate this question. So if you're struggling with the setup in these questions, just know that there's a pretty decent chance the paper will do that for you, if it's anything like the old papers, okay? So here we go, we combine the two fractions on the right, and then we're gonna eventually get up with a times x squared plus 2 is gonna be equal, plus x minus 2 times cx plus d is gonna be equal to x squared plus x, okay? So when you've done a few of these, you don't have to write the step where you combine the fractions and then left-hand side equals right-hand side. You can just say, I know I'm going to end up with this top here being equal to the cross multiplication. Just the numerators, okay? Just saving a bit of time. Now, when we look at this, we are once again looking for convenient values that we can sub into the left and right-hand side of this expression. We could sub in x equals 2 is a good one. It's going to get rid of this. We could sub in x equals 0 is pretty good. It's going to get rid of the c. And then after that, we'll have to make it up as we go. All right, so first thing we're going to sub in is x equals 2, so that the c and d terms are going to be multiplied by 0, and we can just forget about them for now. Okay, here we have 2 squared plus 2, and here we have, again, 2 squared plus 2. So we end up with 6 equal to 6a, which results in a being equal to 1. All right, so we've got a. Now we've got to try and figure out c and d. So like I said, another good value we can use is 0, because when we sub in x equals 0, this c is going to be multiplied by 0, and it's going to vanish. So that is my next move, subbing in 0 on the left and right of this line here. So on the left we get 0. I've subbed in that a is equal to 1, we already figured that out, and we've got x squared plus 2, so we've got 0 plus 2. So here we're going to get just 2. Here we've got 0 plus d times minus 2, so this will result in minus 2d. So we've got 0 equal to 2 minus 2d, and now we solve that equation for d, and we end up with d equals to 1. Okay, cool, we're 2/3 of the way there. We've got a, we've got d, now we've got to figure out c. So I'm just going to write this as a 1, and I'm going to write the d as a 1, okay? A is 1, so is d. Now, if we're looking for clever values to sub into this expression here to find c, well, c is the only constant left, so you can really sub in any value you want and just solve the equation that's left over. I'm just going to pick an easy one. I'm just going to go with 1. I'm going to sub 1 into the left and right hand side. Okay, so we've got 1 squared plus 1 equals 1 squared plus 2 plus c times 1 plus 1 multiplied with 1 minus 2. Like I said, there are a lot of steps, a lot of room for error, so you've got to be very careful with these questions because it's a lot of working out. So on the left we end up with 2. Here we get 3 plus, so we're going to get c plus 1, but it's being multiplied by negative 1, so we've got negative c and negative 1. This works out to be 2 equal to 2 minus c, which only works if c is equal to 0. So there you go, all that work for nothing. All we really needed was an A and a D. Who needs B and C after all? So like I said, that's the hard work done. Now we know what now we know what these constants are. We can substitute these values up here. So we had A was equal to 1, we've got C equal to 0, so this X is nothing, and we've got the D equal to 1 as well. So now we just need to integrate these two fractions. Alright, so staring at these, it should be obvious that this one is once again a logarithm, but how are we going to integrate this one? You've got 1 over x squared plus 2. For this one we can use inverse tan. Okay, we've got x squared plus a squared, so we need a up top. So we don't want a 1 here, we want a square root of 2. So I'm going to magically put 1 up there. So root 2 here, and then 1 over root 2 out the front, and now it's looking more like our standard integral for inverse tan. So we've got logarithm of x minus 2, and then like I said, 1 on root 2, tan inverse of x over a, where a is your thing up top, plus your constant. Alright, there you go. Quite a lot of work and a lot of room for error, so be very, very careful. And yeah, just make sure you're setting them up correctly. If you've got a quadratic term on the bottom, you need a linear term, so an ax plus b, or whatever letters you want apparently, up top. Okay? Alright, and for the next one, this one's a bit of a tricky one as well. We're going to take a different approach to this, and you'll see why in a second. So luckily, it's already been factorized for us, so we can split these apart. And once again, our two terms on the bottom are both quadratic, which means our top terms need to be linear. Okay, the top is always 1 degree less than the bottom. Now when we do our cross multiplication and we make the bases the same, we're going to end up with x squared minus 2 equal to ax plus b times x squared plus 4 plus cx plus d times x squared plus 1. Alright, cool. Now the problem with this, which you may have already spotted, is that there's not really any convenient values we can sub in. We could sub in x equals 0 to get rid of these two, but there's nothing we can sub in here that's going to get rid of this entire term or this entire term. Okay, you can't sub in anything here that's going to get rid of the plus 4 unless you want to use complex numbers, which we don't. So for this one, I'm going to show you an alternative method that I use for tricky questions like this, where there's not really convenient numbers to sub in, so we do something else. What we're going to do is expand this entire right hand side. Okay, so we're going to expand out the whole thing. So we got ax cubed, we've got 4ax, we've got bx squared and 4b, and same thing over here, we've got cx cubed plus cx, dx squared plus d. Now we are going to rearrange this right hand side. We're going to write it like this. Okay, I'm going to group together the x cubed terms together. So I've got the x cubed a and the x cubed c, which factorizes to x cubed a plus c. Alright, so I'm putting these two terms next to each other and I'm factorizing. I'm doing the same thing for the squareds. I'm putting the bx squared and the dx squared next to each other and factorizing. Then I put the x terms, the 4ax and the cx next to each other and I factor out the x. And then I put the constants together. So I've written this essentially as a polynomial of decreasing powers. I've got the x cubed with the coefficient, x squared with the coefficient, so on and so forth. Okay? The reason why I've done this now is because we can compare both sides and say, well, if these two are going to match up, then the coefficients of the x cubes are going to match up, the coefficient of the x squares are going to match up, and the coefficient of the x's are going to match up, and the constants, okay? So from this, we can form some simultaneous equations, which in this case are pretty simple to solve, and we can go from there. All right, so comparing the left-hand side, this has just got x squared and a constant. So the coefficient of the x cubed is nothing. So a plus c must be nothing if these two sides are going to be the same thing. If the x squareds are going to match up, it means that the b plus d needs to be 1, okay? Because you go x squared times 1 gets you x squared. There's our second equation. Third one is the x's, and once again, there are no x's on the left, which means that the coefficient of the x is 0, so 4a plus c is 0. And now the 4b plus d, which is the leftovers, the constants, that must be the minus 2. So now we have 4 equations to solve. Okay, luckily they're kind of in pairs. We've got the a and c, and we've got the bd, bd. So we can just solve them separately. First of all, if we do the a plus c equals 0 and the 4a plus c equals 0, you might have already spotted this, but if I subtract the two, I'm going to get 3a equals 0. So a is 0, which means that c is 0. So the only solution for these two here is both a and c being equal to 0. Okay, nothing else works. Which is convenient. It's going to make this equation up here a lot simpler, which is going to make the integration much simpler. Now if we solve the b plus d equals to 1 and the 4b plus d equal to minus 2, we can subtract the two equations. Okay, so if we do this equation here, take away this one, the d's are going to cancel off and we'll get 3b equal to minus 2 minus 1 is minus 3. We can divide both sides by 3 and we get b equal to negative 1. All right, if I sub that back into here, negative 1 plus what gets you 1? Well, d needs to be 2. Okay, and there is the battle won, okay? The expanding, the collecting, the comparing, the solving, it's all got us to this point where we know how to break this fraction down into two simpler fractions, and because the a and c are both 0, we can do some integration. Okay, so b is minus 1 and d is equal to 2, the other two are 0, so we can now write our integral in this form. Okay, we're writing it as this with b equal to minus 1 and d equal to 2. I'm just going to swap them around because the positive should always be first because I'm a psychopath. And now, how do we integrate this? Well, this one is x squared plus a squared under a. So this is inverse tan of x over 2, and this one is just inverse tan of x over 1, which is just inverse tan. All right, so to be good at these questions, you need to be an absolute pro at logarithm integration as well as your inverse tan, because they're the two most common components for your partial fractions, okay? And don't forget your constant. All right, here we go, last one. All right, and for our last one, there is one last type of partial fractions question we need to cover before I let you guys frolic in the exercises. Here is HSC question from 2011, which is actually the year that I graduated high school. Why did I not do this question? I'll let you figure that out. All right, so what's happening here is when you have in the denominator of your fraction that you're trying to do a partial fraction breakdown of, when you have something that's squared, things get a little bit more complicated. Okay, I'll show you what I mean. Here are some examples. Here is a partial fraction breakdown for just 1 over x multiplying with x minus 1, as we've done previously 4 times. Here's what it would look like if that x minus 1 term was squared. Okay, you have your x, you have your x minus 1 squared, and you also have your x minus 1. Okay, and up top you've just got a, b, and c, all constants. Even though x minus 1 squared is degree 2, you don't need a degree 1 above, you just need a constant. All right, if we had 1 over x squared and 1 over x minus 1 squared, we would have the x squared, the x minus 1 squared, but we'd also have the x and the x minus 1. Now that's pretty confusing. Why are we doing this? Is an answer with a pretty boring and complicated answer. The short answer that I like is that it makes the algebra way more simple. Okay, and you'll see why. Okay, so setting up your partial fractions like this, when you have what's called repeated factors, that's the squares, setting them up like this is going to make your life much easier. So that's what I recommend. Okay. The good news about these questions is in the old HSC course, you weren't expected to know this, and the question would always set it up for you, like in 2011. I'm expecting this will be the same for future tests, but we'll have to wait and see. Okay, so don't stress too much about this because for most partial fraction questions, they do the setup for you and you've just got to figure out the algebra. Okay, so that's what we'll do today. So we will combine all three fractions, and in order to do that, we need to make every fraction have the same denominator. So it's going to look like this. Okay, we're going to multiply this term, top and bottom, by x and x minus 1. So on the bottom, we've got x squared, x minus 1, which is what we are trying to match up with on the left. We'll multiply the middle term, top and bottom, by x minus 1, and the last term, multiply top and bottom by x squared. Okay, now the bases match, we can combine them. And now if we're trying to solve this, now the base on both sides matches, so we can just compare the tops and solve for A, B, and C. This is a pretty nice one because you've got some options of values you can substitute in. We could use 1 to get rid of these two, or we could use 0 to get rid of these two. Okay, we're going to start off by letting x equal to 0. On the left, we still just get 1, and on the right, we've got 0 here, we've got 0 here, so we just have b remaining, and we can solve. So we have b times minus 1, that's equal to 1, which means that b must be negative 1 if we multiply both sides by a negative. All right, that's b done. Now the other good option is, like I said, we can use x equals 1 is what we'll do next. So when x equals 1, we'll have this equal to 0, and we'll have this equal to 0. Notice I've just changed the b to a minus 1 as we're going through. Hopefully that's clear. Now these two terms are 0. We have 1 equal to c times 1 squared. So we just get 1 equal to c. So nice and easy. All right, and now for the last one, we can change this c to a1, so it's just x squared. And now to solve for a, there's only one remaining unknown, which is a, which means you can sub in whatever you want. I'm going to sub in x equals 2 because it's going to turn these two brackets into 2 minus 1, which is just 1. Okay, so you can use any value here, but see if you can pick a number that's going to make your life a bit less stressful. If I sub in x equals 2, I get 2a times 1. I'm going to have minus 1 plus 2 squared. That's going to simplify to 1 equal to 2a plus 3. And now if you made it past year 7, you can solve that and get the value of a equal to minus 1. All right, so we'll go back up the top and we'll change our a, b, and c to our constants. So we just figured out that we had b was equal to negative 1, we've got c equal to 1, and we've got a equal to negative 1. And now that we know that, if we want to integrate this left-hand side, which was the original question, we can just integrate the right-hand side. All right, I'm just going to reverse the order again, so I'm putting the positive term at the front because it helps me sleep at night for some reason. And now we can use logarithms for these two, and for the one on the end, we can use good old-fashioned regular integration by writing this as x to the power of minus 2. So we got logarithm, we've raised the power and divided by the new power, and we've added our constant. And now we can just tie this up a bit, because whenever you have ln plus ln, or if you have ln minus ln, you can use your log laws to make it a bit tidier. So we can write this as logarithm of x minus 1 over x. We can write this as positive 1 over x, and don't forget your plus c, and then you're all good. Okay, so as you've seen, these are quite a bit of work, so you have to be careful with your working out. There's lots of room for mistakes, but yeah, see how you guys go. There are a few different types of examples as we've explored, so it does take a while before you're comfortable with whatever type of question you're going to be thrown into. All right, but if that makes sense, my class can get started on exercise 603 in Maths in Focus, and if you need more examples or help, hit me up whenever. All right, and now to finish off, this is the puzzle from last video, which as of the recording date has not been solved, so you guys are all pretty dumb apparently. This is 10 Jack Queen King, but the Jack and King are above, so it is a high Jack King. Aha, so clever. All right, if you couldn't get that one, this one's a bit easier for you dum-dums. Here is a puzzle. Your hint is that it is a place. If you have any thoughts, chuck them in the comments. Let's see. Okay, thanks very much for watching. Sorry this was a long one, but these questions are quite time consuming. I'll see you guys next time. Thank you.